بسم الله الرحمن الرحيم. Alhamdulillah والصلاة والسلام على رسول الله. Today we're going to learn, we will see and we'll solve an example solving for the equation of motion of electrical system, one loop, and solve for the solution, get the solution. And then we will learn a new term called the time constant. What's the meaning of time constant? Okay, how useful is the time constant? Okay, this is the objective of this example. Okay, and in this example, inshallah, we will learn what do I mean by time constant. Okay, the meaning of time constant. This is the objective of this example. And also we will practice what we learned so far, how to derive the equation of motion of electrical system. Okay, so here, what we're looking for, okay, he said the initial conditions, the meaning of this, okay, he said at t equal to 0, I will close the loop, blah, blah, blah. What does it mean in math terms? He is giving you electrical system, one loop, and he is giving you initial conditions. I at 0, the current at 0, equal to 0. Okay, this is what means switch on at t equal to 0. Okay, so the initial conditions here, given initial conditions, I 0. Okay, solve or find the current I of t. What's the solution? Okay, also find the time constant. Okay, this is a new thing. I will define it next. We call it tau. Find the time constant. Okay, I will show you what does it mean. Let's solve it first. Let's solve it together. What do we have here? We have one loop. Okay, we have a voltage source. This is constant voltage source, like a battery. We have inductor and resistor, and we are assuming current this way, clockwise. Okay, solve, get the equation of motion. So we will use Kirchhoff voltage law. E, the voltage, minus the voltage across the inductor, L di dt, minus the voltage across the resistor, Ri, equal to 0. You can rearrange, okay, take all the negative to the other side, L di dt plus Ri equal to E. Okay, now this is similar to any differential equation you learned how to solve in chapter 2. Okay, take the Laplace transform, solve for I of S. Okay, how you go from this step to this step, Shabab, let me remind you how to go from this step to this step. Okay, partial, fraction, expansion, huh? You know this from chapter 2. Okay, then you go to the table, find the inverse Laplace. This one will be a step function. This one will be exponential e to the power minus this part r over lt. So this is your solution. Now, if you go to MATLAB and solve, plot this solution, okay, this is what you will get. Exponential curve, okay, initial condition or initial value 0, and the final value will be e over r. Okay, all right, this is your initial value, and this is the final value. Okay, in chapter 8, inshallah, we will learn, I will show you a shortcut how to get this. Okay, this is the final value, this is the initial value equal to 0. Okay, now you can use MATLAB, but later in chapter 8 I will show you a procedure how to draw any function, first order or second order system, okay, without using MATLAB. Okay, all right, now we will define a new term called time constant. What is time constant? Time constant, you will need this power value. How much the power? This is the power, right? This is the power. The time constant is the value if you multiply by the power, it will change it to -1. To -1. Okay? So from here, tau will be how much? L over R. Okay? This is the time constant. Okay? This is the time constant. This is the definition, the mathematical definition of time constant. Definition of time constant. Okay. So now we know how to find the time constant mathematically. In the next slide, I will show you physically what does it mean, the time constant. Okay. Okay. First of all, you need to know in this video how to find the time constant mathematically. The time constant, we will call it tau, is the value if you multiply by the power for your exponential. This is your exponential, the power. What is the value if you multiply the power by, it will change it to -1. We call it time constant. خلاص يا شباب? This is what we call time constant. Now physically, what does it mean? Time constant, okay? The time constant is the time it takes. You see, this is the time, right? Response. This is the time. How much time it takes to reach about 63% of your final value. The time it takes to reach for your response, okay, this point, to reach about 63% of the final value, we call it what? We call it time constant. This is the physical meaning. Now, is this true for any exponential? Yes, mathematically proven. This is true for any exponential. If you have any final value problem where you have a first order system, the response will be exponential. The time constant, which is the value, if you multiply by the power, it will change it to -1. It will tell you the time it takes for your response to reach 63% of your final value. We call this time constant. This is time constant. All right. Now this is the problem that we just solved. Okay, we call it final value problem for first order system. By the way, this is a first order system. How do I know this is first order system? Because we have first differential. Okay, we call it first order system. All right. Now this is similar to the problem that we just solved. So the solution for this problem will be similar to this one. So how much the tau here? Tau will be the value, if we multiply by a, it will change it to -1. So it's going to be how much? 1 over a, right? From here, tau will be how much? It will be 1 over a, right? Right? Because tau multiplied by -a, it will be equal to -1. So how much tau? Yes, tau is 1 over a. See how did we get it? All right. What does it mean for final value problem? Final value problem, that means you have 0 initial conditions, for example, and you have a step input. So the function, the response will go to reach the final value, which is equal to the step input usually. Okay, step input. We call it final value. Now, what does it mean here, tau? Tau here means what? The time constant means the time it takes to reach how much? To reach 63% of the final value. Okay? This is the final value. خلاص? Okay? Final value. All right. There is another problem for the same system. What if we do not have a input, at t equal to 0, the switch was on at t before we start before the time, the switch was closed. Okay, the switch. What if the switch not open? It was closed. Switch. For example, here, the switch. Let me write it. Switch at t less than 0 is closed. Okay, it's closed. Okay. And at t equal to 0, open. So it's going to be initial value problem. That means you will have initial conditions, okay? And after that, the current will die out, okay? This system similar to this system, but the initial conditions are different, okay? The initial conditions are different. And here we have a step input. Here we have no input because we opened the circuit, okay? Anyhow, what is my point here? My point, if you solve for this response, you will get this solution. How much tau here? Tau will be, if you use this equation or this formula, it will be the same. However, the meaning here is different. Tau here means what? The time it takes to reach how much? About 37, sorry, 37, not 36. About 37 or 36 is almost the same. About 37% of the initial value. We don't have final value because the final value here is 0. So 37% of the initial value, okay? So tau here is the same as tau here, okay? They are the same, okay? But the meaning or the meaning is different. Here tau, the time for final value problem, the time it takes to reach 63% of the final value. Here for initial value, the time it takes to reach 37% of the initial value, Okay, so what's the conclusion here? What's the conclusion here? Tau or let me rephrase that. For a system, tau is always the same, regardless of initial conditions or input. That means it does not depend. Tau is independent of the input or initial conditions. Is that clear, Shabab? So tau is similar to what? For first order system, tau is similar to natural frequency for second order system. It's a property of the system, okay? It does not depend on the initial conditions or the input. Halas ya shabab? This is the conclusion, okay? This is the conclusion. This is tau, okay? I hope it's clear. Okay, let me write it again. Tau, okay? I'm worried just about when you print it or read it later, okay? It will be clear. I hope it will be clear. Okay? Although it's taking much time. خلاص يا شباب. So tau will not change, even if you change the initial conditions or the input. خلاص? Keep this in your mind. All right. Now, what does it mean? How important is tau? I'll show you how important is tau. Look, let's assume you have two systems, different systems. For system number one, okay, you have this curve, this response. It's initial value problem. And for system number two, different one, you have another curve. This is the different response. Now for system number one, you have tau 1. And for system number two response, you have tau 2. Tau 1 is less than tau 2. What does that mean, tau 1 less than tau 2? That means the system number 1 will decay faster than system number 2. As simple as that. Okay? How important is this? It's many times, or in first order systems, for example, if you have a thermometer, okay, if you have a thermometer, you are in the clinic or you want to see the doctor and you have a thermometer. Thermometer is a first order system. The reading of the temperature of a thermometer is a first order system. Okay, so if you have two different thermometer number one, you bought it from the market, and the thermometer number two, you bought it also different from a different market or different shop. Thermo number one has tau 1. Thermometer number 2 has tau number 2. Which one is better if you want to buy? Thermometer number 1 or number 2? Of course, number 1 will be better. Why it's going to be better? Because tau 1 is less than tau 2. So what? That means if tau 1 is less than tau 2, tau 1 or thermometer number 1 will reach your temperature faster than thermometer number 2. As simple as that. Okay? So it will reach the final value. We call this the final value. It will reach the final value faster. It will take less time to reach the final value. Okay? Which is usually more expensive. Okay? So tau, as I said, is like a natural frequency in second order system. In second order system, when you want to design a second order system like a mass spring damper mechanical system, you will always take care of the natural frequency. You will design your system and take care of natural frequency. Okay, like the temperature. When you go to see the doctor, you are sick. What is the most important number he will measure? Your temperature, right? In second order system, natural frequency. In first order system, tau, the time constant. خلاص يا شباب. We will talk more about it later, inshallah. It will make more sense, inshallah. Okay? For now, you need to know the meaning of tau. What does it mean? How important is tau? Okay? How to find it mathematically? And what does it mean physically? Okay? That's all. Next, inshallah, we will solve more examples. Let me solve this example quickly. How to find time constant from first order system. I will show you the long way, then I will show you the short way. Okay, the long way, solve this problem just like you did in chapter 2. Okay, so take Laplace transform. Take Laplace transform. What is the Laplace transform? Okay, take Laplace transform. Also given here, given initial condition, we need initial condition. Without initial condition, we cannot solve because this is homogeneous problem. X at 0, let's call it x naught. This is given, okay? Take Laplace transform. So this is going to be a xs minus the first initial conditions, right? Oh, sorry, it's s minus what's the initial condition? X naught, yes, plus b xs, okay, equal to 0. So this will be I will show you, this is the long way, then I will show you the short way, okay? I promise, inshallah. A x naught plus b, okay, b xs. Now all you have to do is solve for xs. This will be how much? This will be as plus b xs equal to a x naught, okay, where xs equal to a x naught over as plus b. Okay, you can simplify this more by dividing by a. This will be x naught over s plus b over a. So I go to the table now. Okay, go to the table. What will be x of t? Solution, which is the inverse Laplace of x of s. If you go to the table, it's going to be x naught e to the power minus b over a times t. So how much tau? It's equal to the value. Okay, tau is the value if you multiply by the power minus b over a. It will change it to minus 1. Therefore, tau will be how much? It will be how much? A over b. Okay, this is the time constant. Is there a short way? Yes, there is a short way. Okay, what's the short way? I will show you. Let me write it in different color because you're going to need it later. Okay, the short way. Let me change the color to blue. Okay, rewrite your equation in the standard form. How are you going to rewrite? Divide by the coefficient of x dot. Okay, so this is going to be x dot plus b over a, divide by a, okay, x equal to 0. Okay, you see this form? We call this the standard form. X dot plus tau. Oh, sorry, I did the opposite. Sorry. I confused with the second order system. This is not second order system. First order is different. Sorry about this. Okay, this is for first order. What's the standard form? Equation of motion for first order system. Divide by the coefficient of x, not x dot, x. So this is going to be a over b x dot plus x equal to 0. This is the standard form. Tau x dot plus x equal to 0. What is this? This is the equation of motion. Equation of motion of first order system in standard form. Why we like to write the equation of motion for first order system in standard form? Because from here you can know directly how much tau. So how much tau from here? How we got it from here? It's A over B. Is it the same or not the same? A over B, it is the same. See how much, much less effort to get tau from here. Okay, that's why we like to write it in the standard form, because always as a control engineer, when you want to control your first order system, you want to take care of tau. You want to measure how much tau, and then you design your system, control it. Okay, so that's why we like to write the equation of motion in the standard form. This is for first order system. Okay. Okay. All right. Let me finish with this slide. I ask you one last question. Second order system, do they have a time constant? This is second order system. By the way, let me review this with you. How to go from here to here? Okay, this is what we call it. This is the equation of motion of second order system in standard form. Why we like to write how to go from here to here? You divide by the coefficient of x double dot m. Okay, then you get. Why we like to write the second order system in standard form, the equation of motion? Because we want to measure directly how much natural frequency, and also zeta, because you're gonna need these two terms when you want to control your second order system and you want to design it. Okay, now let's go back to my question. Time constant for second order system. Is there a time constant? It depends. And depends on what? If you have exponential in the solution, then you will have time constant. Okay? If you have exponential, so how much the value, if you multiply by this power, it will change it to -1. It will be 1 over zeta omega n. So it depends on the solution. If you have exponential in the solution, you will have tau. However, time constant for second order system is not as important as it is for first order system. We need time constant always when you want to control first order system. For second order system, what's the most important terms? As you can see from the equation of motion, natural frequency, okay, and the damping ratio. We will talk more about it inshallah later when we come to the analysis, okay? So we're going to stop here, and next inshallah we will solve more problems. Okay, thank you very much.